Thank you very much to the organizers. Well, it's for me a first to give a conference talk online. Also, I've had by now many lectures online. Okay, I'm going to talk about joint work with Wan Chopeng of Nanjing University. And our problem is hyperbolic boundary problems with totally characteristic boundary. So we basically we are interested in our first order n/n systems of that form as shown here. This is, so we have the t derivatives, then we are in a half space, so we are doing the local model if you want. Also everything is going to be coordinate invariant, so you can easily implement it on manifolds. And the point is, so if we call this factor here the x times a naught, say, that is the boundary matrix, if you want, and this matrix is assumed to be 0 along the boundary. So then you can pull out this factor of x, which I've done. And so people familiar with say cone-degenerate TwoDimensional operators can probably guess what I'm going to do. I just consider this as a cone-degenerate problem. So first of all, or maybe I should say hyperbolic. I should explain. This comes later. Yeah. So as written, this system is neither hyperbolic nor anything. But so suppose we have just fixed our hyperbolicity condition. Then in that case, the number of boundary conditions to be imposed is always the number of incoming characteristics. Here, all characteristics are tangent to the boundaries, so nothing comes in, nothing goes out, so there are no boundary conditions. Which then also means, and this is sort of the idea, we can treat that as a Cauchy problem. Okay, then so I allow for the solutions to have asymptotics of that form, so very well known from the theory of cone-degenerate operators. So we have some powers x to the p for cosmetic reasons. I put a minus sign here, and we have certain logarithms, and then we have coefficients. And this prefactor here is just that formulas work out correctly. So so I'm going to introduce certain spaces h as delta p zeta, so depending on 4 parameters on this closed half space, or on the half space, where S is Sobolev regularity, delta is some basic weight or conormal order, P is this asymptotic type, which basically collects the P's and the K's appearing here. And zero is some improvement in the weight, it's just basically subtracting these asymptotic terms from the solution. We improve that conormal order from delta to delta plus zeta. So the zeta is a non-negative number. So these results sort of were already obtained by Reiko Sakamoto in a say smaller class of function spaces. So here she has 3 parameters. So I just write it in the way I'm going to use it later. So in case delta is 0, or then the space is nothing else but the usual HS space. And for any other delta, it's essentially x to the delta times HS. Okay. What is really new is that we show that these boundary traces, so these coefficients, gamma pku, that they solve hyperbolic Cauchy problems themselves in the boundary. So they can sort of basically found prior to solving the equation. So possible are extensions and applications. So first of all, of course, there's a long-standing open problem of treating hyperbolic problems with characteristic boundary of constant rank. So if the boundary matrix has maximal rank, then the non-characteristic case, this case is sort of understood by, for instance, both the uniform density condition. now we are at the other end, and then there are some results in between, but so there is no final definite result set. So maybe this work can contribute to that problem. So what we are really interested in are the compressible Euler equations with a vacuum boundary. We have just written that equation with the usual meaning of the symbols. Rho is mass, V is velocity, E is internal energy, P pressure. And then we have some derived quantity, which is our speed of sound. So if you have a moving vacuum interface, yeah, then this speed of sound behaves like x to the 1/2. Yeah, so where P is -1/2, so we have just a case where we are not in the framework of Sobolev spaces. Actually, we are interested more in a situation where one has a stationary, as a non-moving vacuum interface, then x behaves like, C behaves like x. So what seems to be still again in the framework of Sobolev spaces. Looking more carefully, that is not true. Yeah, so the density behaves like x to the 2 over gamma minus 1, where gamma is the adiabatic constant. So in the most cases, this is not an integer, and one can also easily produce examples in applications where one has log terms. So therefore, we just decided to treat it as a more general case. Okay, so once I've told you what the hyperbolicity condition is, then so this will be our symmetrizable hyperbolic in this degenerate context. We need an appropriate two-dimensional calculus to symmetrize the system here, and this is what I'm going to introduce next. So first, so we start with function spaces. So some of you might already know this, so I will be quick about that. So we started with weighted Sobolev spaces in the half space R1 plus D plus, R1 plus D and sub plus. So it depends on two parameters as gamma, and in case that S is a non-negative integer, upside, what is that here? The definition is here. You can see that in that line. And then for general S in R, we get the spaces by interpolation and duality, or using the Melling transform. And then, so basically, we are interested in mostly in the behavior close x equals 0. So at infinity, basically we can do what we want, and convenient setup is just to require standard Sobolev behavior if x is large. Yeah, so we implement this using such a cutoff function. This gives us the spaces K is gamma. Okay. So for the following, we just fix some basic conormal order delta or some weight information, and then this space K0 delta would serve as our basic Hilbert space. Yeah, if delta is 0, this is the usual L2 space, and now we just take that one. If we form adjoints and so on, we do it always with respect to this Hilbert space. So now I should tell you what an asymptotic type is. So basically, this collects the information on the P's and the K's in the asymptotic expansions. So so I'm not going to say what an asymptotic type is, but I'm just saying it's given by discrete subset of the complex numbers contained in a left half space. So here we see this delta, and then the real parts of the P go to -1 as modulus of P goes to infinity. This is due to the fact that we write the exponent as negative P instead of P. And then the third condition, which is listed here, is needed to get coordinate invariance. And then basically I just write the asymptotic types as sets. Yeah, so P is in that set PCP, and the K is less than the multiplicity of P. Okay, so and now I organize things as a cone two-dimensional calculus. This, but I have basically to adapt a situation slightly. So in the cone pseudo-dimensional calculus, this W usually is a smooth function. Not in our case. Yeah, this W is something like the trace. If you have Sobolev spaces, traces from functions taken from Sobolev spaces are not smooth. Yeah, and then we cannot write it as such a tensor product. There's a function of X times a function of Y, but we have to do something more sophisticated, and we are going to replace here this red guy by this green guy. Yeah, so if we have K log terms, we need this W, this coefficient from basically from some space HS, which is slightly smaller. Yeah, this is here just the definition smaller by this log term. Okay, and then you see, so we have this regularity as closer we get to this critical weight. As more regularity we lose, and if you just take here the differences with the guy we are interested in, we sort of swap to the other side, and now we have this here with the opposite sides. Okay, then we basically introduce a corresponding potential operator gamma pk. So it starts with a W, produces a function of X and Y. So I can disregard the T dependence that comes later. Yeah, so a function in a half space. Here I introduce this prefactor we previously had, and that is just the definition. And then we get these function spaces I mentioned. So we have some Sobolev order S, we have an asymptotic type T, which comes with this fixed polynomial order delta, and we have an improvement of this polynomial order by zeta. And then now you know regarding asymptotic terms, so if you have Sobolev spaces, the order of which is a half integer, so they are exceptional. Yeah, and the same phenomenon we have here, so we have just to exclude those zetas, yeah, from the consideration at first, but this is a discrete phenomenon. In the end, we get the whole scalar by complex interpolation. So that's not a big deal. So we can assume this here. And then we introduce the space H as delta P zeta as a space of all U and K as delta, for which there are corresponding traces having the correct regularity, such that if you subtract those asymptotic terms, we improve the polynomial order. So there's a price to pay, which is here, but this is also not a problem. So that's the corrective. This is the correct definition is shown by the example. So first of all, maybe I should say, so these boundary traces, they are denoted in that way as before. Yeah, so if you just take P, the asymptotic type to be the type P naught, which is the one which results from Taylor expansion at x equals 0, and we take zeta to be S and delta to be 0, then we have the usual Sobolev space. The same is, so with the same parameters, but the asymptotic type is the empty asymptotic type, meaning that PCP is empty. We have these supported Sobolev functions. Yeah, so functions in HS on whole space are 1 plus D having support in this closed half space. Yeah, so these standard cases are included. Okay, so now very quickly, for the class of two-dimensional operators. So if depending on from which school you come, either you call it cone calculus or B calculus. So here it is, we need some adjustments. Yeah, I just take all classical coordinate two-dimensional operators with the additional requirement that I allow only holomorphic convolutional symbols. what is such a economical symbol? So if I write formally the operator in that way, and here I have this totally characteristic derivative, then I get the economical symbols here. So basically to any negative order, just by doing Taylor expansion at x equals 0. And then it depends on that complex parameter, z. Usually, or initially, it lives on the real part z is 1/2 minus delta for that fixed delta. Typically, one has, well, then basically has a meromorphic extension to the whole complex plan, and we just require those not to be meromorphic but holomorphic. So, and maybe I should say why that is possible. So one could also think that we have now a cone over this non-compact manifold RD. This might be a problem. Also, the holomorphic economical symbols might be a problem. Well, it is actually not in that given case, because symmetrization of our hyperbolic system requires neither an inversion nor a parameter construction for any elliptic operator. Here, and we just need the compact base or say meromorphic economical symbols if you want to do either of that. So we don't have to do that. Yeah, and therefore we can this makes this assumption that the economical symbols are holomorphic. Then we have the usual elements of the calculus. So proposition stays in the class. Plus we have symbolic rules. For the principal symbol, I'm going to show you a notation for that on the next slide. The adjoints belong to the calculus as well, and we have the mapping properties. Actually, here for all SD, delta, P, and zeta. So the only thing is what we have is here the order shift due to the order of the operator. Everything else is untouched. Yeah, there's also a consequence here that the P is not changed. Is also a consequence of the holomorphy of the common symbols. Okay, so what is then the result? So now we write, instead of a differential system, we write it as a pseudo-differential system. So we take A to be our smooth in T, and taking values in the class just introduced. Now Cn means it takes vector functions to vector functions. So we have a system. Otherwise, it is just the same as before. And now we need to assume, or now we need to say what I mean by hyperbolicity. Well, so so the principal symbols of operators here, they live on not exactly on the cotangent bundle, but on we call it the compressed cotangent bundle. The point here is we have an intrinsic description of all these possible principal symbols for operators in that class. Yeah, and now we just take such a possible principal symbol B. Yeah, that is basically a function essentially on the cotangent bundle, taking values in matrices, and we want that this has two properties as pointwise, and actually this not only depends on T, but here also on the variables in here. This pointwise positive definite, so it's a matrix function, and when multiplied with a principal symbol of our A, we get something which is skew emission. Okay, so we make that assumption. And then here's the result. So we assume that the initial condition belongs to HS delta P zeta. F is, say, in L1 with values in HS P delta zeta. Or we can also allow more time derivatives, and we get also more time derivatives on the solution. So then the result is, okay, so there's a unique solution. So U in which is continuous in time, taking values in HS delta P zeta and correspondingly for time derivatives. So, and what is basically then now the really new thing is here, all these boundary traces. they also satisfy basically systems of hyperbolic equations on 0 cross T cross RT. And these are basically classical pseudo-differential systems, hyperbolic systems. Yeah, so we have the T derivative here, we have the spatial part here, we have the trace coming from the right-hand side, and here we have something which has previously been computed. Yes, the initial condition is just a trace from the initial condition. And that this system is hyperbolic follows from the fact that hyperbolicity only depends on, so as defined, only depends on the principal part of the operator A, or this is now here Z operator. First of all, and then we have this compatibility condition between the principal symbol of A and the principal symbol of as leading conormal symbol evaluated at the point P. Okay, so that is hyperbolic. This can be solved. So, and now in the last few minutes, let me just briefly indicate the proof of the results. So what we need to do is we need to establish an a priori estimate, so assuming a bit more regularity so that everything in this estimate makes sense, and we want to show this inequality, the red one shown here. So matter of fact, we can assume that S is 0, so there are order reductions in the calculus, and then we just proceed in 2 steps. We first treat this the case without asymptotics, so 0 is 0, and then our spaces are just the K not delta spaces, our basic Hilbert space, and then we allow asymptotics. So for the first thing, so one sort of uses a Gaussian inequality to just turn this symbolic symmetrizer into a true symmetrizer for the system. So that is here the same condition as before, but here it's just that this is basically positive definite for every T. And so we can do this, we can choose such a B, this is just given principal symbol. And then we are in the standard framework of proving well-posedness of a Cauchy problem in full space. So here, these are the 3 things one needs. So first of all, this BTVV is an equivalent norm on our basic Hilbert space. Yeah, this is just equivalent to the original one uniformly in T. This follows from here, and oh sorry, and it's the fact that the B is of order 0. Then the next thing, which makes it actually a Cauchy problem, is that an integration by parts do not produce any boundary terms. And the reason is simple. So here, that is the way how we introduce the formal adjoint of A. So this equality is valid for all test functions, for all smooth functions supported away from the boundary at x equals 0. But if we basically disregard the asymptotic terms from the considerations, then the test functions are dense in that space. So this equality carries over to U and V as shown here. Yeah, so we can do an integration by parts, we get no boundary terms. And then the imaginary part of that operator is of lower order. So one needs these 3 things, and standard arguments goes through also in our situation. So now, basically, second thing, we allow asymptotic terms. So first of all, we can generically, we can assume that we are in the generic situation. So we are here. Yes, as we get the general case by interpolation, just to short notation, we write U at 0 at U naught, and this DTU plus AU as F. So then we first basically compute the boundary traces. As we have seen that they satisfy hyperbolic problems, and so we can solve these hyperbolic problems, and what we get, so we get these boundary traces with the correct regularities. and with the correct estimates. So then next step, so basically we just consider, my gosh, my computer is slow here. Okay, so then we basically are, so having computed the boundary traces, so we apply this potential operators, takes the differences. So we do it for the initial condition, we do it for the right-hand side, and then we are left with a hyperbolic system. But now the initial condition is an hs minus zeta, comma delta plus zeta, actually a little bit better, but this doesn't matter. And the f bar is in L1, this is in hs in ks minus zeta delta plus zeta. But this is something we can already solve. So we just solve that. That's the same estimate, and finally we just observe that. So our true solution is just the sum of these two, and putting all these estimates together, we get what we wanted. There, and so basically my time is up. That remark, I'd like to stop, and I'm prepared to answer questions.
Thank you very much for this interesting talk. Are there any questions? Comments?
I'd like to ask a question. So suppose that you have not only the 1x variable, which is degenerating, so but suppose you have a kind of wedge, you know, so you have more than one.
Well, this is kind of a wedge, actually.
No, but anyway, so suppose that you have more degeneracy. I mean, other variables that are degenerating.
Okay.
So so do you think you can?
Cannot answer that question. So so our main focus was on this vacuum problems in fluid dynamics, and this is exactly the situation we need. So it might, yes, I guess one can do something, but I don't know. I haven't thought about that, so it's.
Okay. Any other question? Well, if not, let's thank the speaker again. And